All right, now we'll talk a bit about electron transfer. We're ultimately going to talk about two different mechanisms for electron transfer. First one we'll talk about is outer sphere electron transfer, and we'll often talk about these self-exchange reactions. And they're self-exchange because we have two reactants. But when those reactants react, we get two products which are identical to the two reactants. So we have an iron 2 hexaaqua complex and an iron 3 hexaaqua complex. We're going to have an electron transfer from the iron 2 center to the iron 3 center. We've marked what originally was the iron 2 center here with an asterisk. And so the iron 2 center becomes an iron 3 center, and the iron 3 center becomes an iron 2 center from the electron transfer. And from this, since we start with two reactants and we end up with the same two products, we have a free energy change of 0 here. Okay, this is not exothermic or endothermic. This is a thermoneutral reaction. The two complexes, the green one here being a reductant and the blue one here being an oxidant. The electron is transferred from the reductant to the oxidant. Then the two complexes diffuse apart, so both of these are moving around constantly in solution. They need to bump each other at least for a second for this to happen, and then they can diffuse back to anywhere in the solution. We don't have any ligand loss during this process, so these 6 waters are firmly attached to the green complex, and these 6 waters are firmly attached to the blue complex. Most redox reactions in biology are believed to occur by this mechanism, and this Marcus theory was the basis for the 1992 Nobel Prize in Chemistry. All right, so we want to examine the prospect that the products are formed with the geometries of the reactants. And if we look at the ionic radii, which will give us some estimate of the iron-oxygen bond lengths, the ionic radii for iron 2 versus iron 3 is different. And what we come out with for this is the ionic radius for iron 2 is longer. And so all of the iron-oxygen bonds are longer in the iron 2 complex and relatively shorter in the iron 3 complex. So if, and this if is bolded on purpose, if the reactants are in their ground states, the products would be formed in excited states. And let's see why we're making that statement. So if an electron transferred from this iron 2 center to the iron 3 center, we would have iron-oxygen bonds that are too long for an iron 3 center. And for what's now the iron 2 center, these bonds would be too short. These complexes would then need to relax and release energy. Okay, so this bond length would need to shorten, this bond length would need to lengthen. But that can't happen because we know that delta G is equal to 0. The free energy is equal to 0. So it would seem that we've created energy from nothing, and a reaction could not be occurring between the two ground state structures then, because this process would lead to the creation of energy from nothing. Okay, so what does happen then? There must be an activation step which precedes the electron transfer. And so we've got these two complexes just hanging out in the solution. The iron 2 with the longer bonds, the iron 3 complex with the shorter bonds. And what's happening is just from the thermal energy in the room, the bonds are vibrating. So these bonds are becoming shorter and longer constantly, shorter and longer constantly. And what needs to happen is we need to get to a point where the green complex bonds have contracted and the blue complexes bonds have expanded exactly the same instant, so that the two complexes are identical. So a squeezed in green complex and an expanded blue complex have gotten to the point they have exactly the same energy and exactly the same bond lengths. Then the electron transfer can happen. Okay, the electron moves from the iron 2 center over to the iron 3 center. Now the relaxation happens, and that's okay. Whatever thermal energy we had in the flask from just the temperature in the room that was needed to cause this process, the activation energy, is exactly equal to the energy that's released when the complex is relaxed. And so since the activation energy and the relaxation energy are equal, we're all right with the free energy being 0. Okay, the activation step involves making the bond lengths in the oxidant and reductant the same. So both of them have to be adjusted. If the oxidant and reductant have very different bond lengths, the activation energy will be large and the reaction will be slow. If the oxidant and reductant have similar bond lengths, the activation energy will be relatively small and the reaction will be fast. So we need to compare bond lengths in the oxidant and reductant to understand the rate of the reaction. So metals get smaller as we go left to right with increasing Z across the periodic table. However, occupation of the top 2 orbitals, the Eg star orbitals, lengthens the bonds. And then finally, metals in the +3 oxidation state, for example, will be smaller than the metal in a +2 oxidation state due to the difference in charge. All right, let's go back to our 5 lines here, like we've used many times for crystal field stabilization energy and so on, and prove to you that this occupation of the Eg star, the top orbitals, lengthens the bonds. So we have a D0 complex. We go to a D2 complex here. We put 2 electrons down here in the bottom. And when we do that, the bond has gotten shorter. This is the bond length that we have here. The bonds have gotten shorter. When we occupied the T2G, we add a 3rd electron and it continues. It gets shorter. Now, if we go to D4 high spin, we've put the 4th electron into the Eg set. And so the bond has actually gotten a little bit longer. So we got shorter and shorter, and now when we've occupied Eg, it got just a little bit longer. When we put a 2nd electron in the Eg set, it gets even longer. Now the next electron goes into the T2G, so the bond shortens as we would expect it to. We go to D7 high spin, so we put another electron in the T2G set, it gets shorter. Now D8, we put another electron in T2G. Now we start to occupy that Eg set. Okay, so we go from D8 to D9. We put an electron into the Eg set and the bond got longer, and we put a final electron in the Eg set and it gets longer. Okay, and here we're comparing our D0, D5, and D10. Here we have no electrons in the Eg set. Here we have 2, and here we have 4. And along this set, we see, if we compare D0, D5, and D10, that the overall trend is that the bonds get shorter. However, occupying the Eg set leads to a shortening of the bond. All right, here's to add in the low spin complexes, so low spin D4. So compare high spin versus low spin D4. The low spin D4, the bond is shorter. D5, D6, D7, and D8. All right, not a whole lot for you to get from a comparison of these two, except to compare some individual points. So for example, if we look at D3, D3 for a +2 metal versus D3 for a +3 metal, you'll notice that the D3 for the +3 metal is significantly shorter than the D3 for the +4 metal. If we go through and look at the different points, we'll see that. Okay, and as stated earlier, the +3 charged metals are smaller than the corresponding +2 due to the higher charge. And then we see things like this. So if we were to go and sketch in the levels, so iron 2 hexaaqua complex is D6, iron 3 hexaaqua complex is D5. Both of these are high spin. In going from the iron 2 to the iron 3, we are removing an electron from the T2G set, from the bottom 3 orbitals. So removing an electron from the T2G set to do this transfer leads to a metal oxygen distance change of 13 picometers. We get a rate constant of 4. Well, we need something to compare that with. Here, comparing chromium 2 hexaaqua complex, which is high spin, and chromium 3 hexaaqua complex, which is D3. Here we are changing the EG electrons. We're removing an electron. In doing this oxidation, we're removing an electron from the EG. This leads to a larger change in the bond distance and correspondingly a significantly slower reaction. Okay, the rate constant here is 4 versus 2 times 10 to the minus 5. A different, faster mechanism can operate sometime, and this is called an inner sphere electron transfer. Either the oxygen or the reductant must possess a ligand that's capable of bridging the two metal centers. Okay, that means that it has at least 2 lone pairs in the ligand. And the other reactant must be labile. It must be able to open up a site on itself. So here's the classic reaction for this. We have chromium 2 hexaaqua complex. We have this cobalt 3 complex, which has 5 waters and 1 chloride. Well, the chloride is using just one of its lone pairs to bond to cobalt, so it has available 3 other lone pairs that could bridge to a second metal center. So if we go to the chromium center, and it ends up that this is a D4 high spin complex. This D4 high spin complex is very labile. It loses a water and gets coordinated by one of the lone pairs of the chloride. It forms a bridging complex. So right now we still have chromium 2, cobalt 3, with a chloride here in the middle, and then everything else is a water. So we have 2 plus and 3 plus, that's 5 plus, and a minus 1 ligand is how we get this 4 plus overall for this complex. So this is called an inner sphere complex. It's bridged by the chloride ligand. Now what can happen is the chromium 2, chloride, cobalt, the electron can hop from chromium 2 cobalt, and we've got now chromium 3 chloride cobalt 2. Okay, the chromium has lost an electron and the cobalt has picked up that electron. Still, the whole complex has the same charge. Okay, so 3 plus, 2 plus, and 1 minus gives us 4 plus overall. But the complex now can come apart and the water can come back. And so what we're left with is here at the end chromium 3 with a chloride. So plus 3 minus 1 gives us 2 plus overall. And now it's cobalt with 6 waters, cobalt 2. So what's happened overall? We've had chromium 2 become now chromium 3, and we've had cobalt 3 become now cobalt 2. A really neat thing with this particular reaction too, you should notice, is the chromium makes off with the chloride. So the chloride was attached to cobalt. At the end of the reaction, the chloride now is attached to the chromium center. This so-called inner sphere reaction is possible because chloride has more than 1 lone pairs, so it can use its lone pairs to bind simultaneously to chromium and cobalt to form an inner sphere complex. What was also necessary is that chromium 2 is labile. It's D4. It's Jahn-Teller distorted, and the water ligands that are attached are very labile. But you should note that once the electron transfer has occurred, it is the cobalt 2, which is labile, and chromium 3, which is inert. Therefore, the bridging ligand leaves with the chromium 3. Here again being the crucial step. We've done the electron transfer, and now the chromium has made off with the chloride, and a water from the solution comes in and attaches itself to the cobalt.